Hey guys, so this is me and Jack. We're going to talk about stability of nonlinear systems. Um, so stability, actually let's call it even better, say Lyapunov stability. Okay, so a lot of people call this Lyapunov stability. Some people just call it asymptotic stability, um, but leverage a lot of the theory that Lyapunov developed. So this is just going to be a slew of definitions. Um, let's write that. So these are definitions for asymptotic stability. Great. So the first thing that we're going to talk about is the notion of stability itself, um, which so previously we've talked about stability as being kind of two sides of the same coin. Now we're going to talk about each of those sides independently of each other. So you can, for instance, have one component of asymptotic stability without the other, which is stability and convergence or attractivity. So for stability, we say that an equilibrium point, x star, is what's called stable if there exists an epsilon greater than 0 and a delta greater than 0, such that x of t naught minus x star, the norm of that, is less than delta, implies that the solution is less minus the equilibrium point, and the norm of that is less than epsilon for all t greater than the initial condition t. So this requires two scalar values, epsilon and delta. And if we start, basically, if we initialize a solution less than delta, this will imply that all solutions are less than some value, are close, are epsilon close to some value. So basically, if you start close, you stay close. Okay, so I'll write that here because it's a great way to remember what stability is. So let's write this in another color. Say start close, stay close. All right, so the next notion is this notion of convergence. So an equilibrium point is convergent or attractive better than my couch. If again we start the initial conditions nearby the equilibrium point, so if there exists this delta greater than 0, such that the difference between the initial condition and the equilibrium point is less than delta, and the limit as t goes to infinity of the solution x minus x star is equal to 0. Or equivalently, if if the limit as t goes to infinity of x of t equals x star. He's trouble. All right, and though if we have attractivity and we have stability, then we say that we have that our system or our equilibrium point is asymptotically stable. Okay, so this should be 2, this should be 3. So again, this equilibrium point is asymptotically stable. Let's capitalize that. If it is both stable and convergent. So if we have these two properties, we have stability here, so we have bounded solutions, and we have that all solutions converge to the equilibrium point, then we get asymptotic stability. Okay, great. So next, we can also talk about maybe a stronger form of asymptotic stability, namely if we converge exponentially fast. So asymptotic stability doesn't necessarily imply a rate of change to the equilibrium point, but if we can show that we have an exponential rate of convergence, that's a much stronger result. I think he lost his ball. Jack, go get another ball. Okay, so an equilibrium point is exponentially stable He's pissed. Go get your ball. Okay. It is exponentially stable if there exists delta greater than 0, a lambda greater than 0, and an alpha greater than 0, such that if we start our initial conditions nearby the equilibrium point, so a delta distance away from the equilibrium point, and the solution is upper bounded by, oops, not delta, alpha, but upper bounded by this exponential function, decreasing exponential function relative to t and this value lambda. So this gives us a rate of change in the exponential sense. So it's saying that if we have the solutions, the distance between our solution and our equilibrium point is upper bounded by this function that is a function of time, and so it decreases as time goes on, and it decreases at a rate of lambda. Okay. So what do these mean? If we have an equilibrium point, let's see the best way to draw this. So if we have an equilibrium point, let's say there. Can you see that? No. Make it bigger. So if we have this equilibrium point, x star, and we have this delta ball and epsilon ball around it, Okay, so now this is a delta. This is an epsilon. You can't see that yet. What the heck? Okay, let's resync this. Okay, great. Now you can see it. All right, so if we have a delta ball around our equilibrium point and an epsilon ball around our equilibrium point, this is just oh man. I think he lost his ball into the couch. Then if we start a solution, let's say, let's color it blue. If we start a solution right here, okay, so it's within that delta ball, and this solution kind of stays, evolves over time and stays inside this epsilon, then we can say that we have what? Stability, right? However, if we take a different system, or maybe design our controller a little differently, we can take another solution from this point, still within this delta, and we can, this guy maybe oscillates a little bit out here, but eventually converges to the equilibrium point, but doesn't do so in an exponential way. We have convergence, okay? So with this green one, we have both convergence and stability, since it stays inside this epsilon bound. It starts within this delta bound, and it converges to the equilibrium point. We get asymptotic stability. There may be cases where you have a solution here, but you don't know what you can't bound it above because of the properties of the solution. So it may explode, but at some point in time, larger than the explosion time, it'll come back and converge to X star. Okay, so in this case, we don't have boundedness of solutions. So you're not, if you start close, you're not staying close. So you would just you would just be able to show convergence in this case. To compare exponential stability and asymptotic stability. So say we have, the easiest way to look on that is if we have time and we start our solutions right here, let's say right here, delta. Then if we would expect our epsilon, the function, the exponential function to decrease exponentially for exponential stability. However, for just asymptotic stability, it might decrease. Actually, it may increase a little bit and then decrease. So we wouldn't be able to necessarily upper bound it by an exponential function. We would be able to upper bound it by some other function. And this would also converge to 0. If this is the distance of our solution to the equilibrium point. Nice. So next we're going to talk about, so those are the definitions of stability. Namely, remember we have asymptotic, we have stability, we have convergence, we have asymptotic stability, and we have exponential stability. Note that these are all local notions. If we wanted to make it global, what would we do? Well, we would remove the conditions on the assumptions on the initial conditions for the convergence. So if we can show that we can converge from any point in our state space to the equilibrium point, then we have a global attractivity, which implies if we have stability, and because stability is just a local notion, and the global notion of attractivity, then we can say we have global asymptotic stability or global exponential stability. Again, if for global exponential stability, if we can remove this bounded, if we can move this condition on bounding the solution, the initial conditions of the solution, then we can say we have global exponential stability. All right. And so next time we'll talk about how do we show that we have exponential stability, or how do we show that we have asymptotic stability?